All right, this video is going to be about meso compounds, not like meso, like mesosphere, but meso, like meso compounds. These are compounds with two or more stereogenic centers, and you might be thinking diastereomers, but they're achiral. Say what now? What you talking about, Jess? Well, they're achiral because of symmetry. So remember, there is for n number of stereogenic centers, you have 2 to the n possible stereoisomers. Well, if there's symmetry, then that's not going to be that's going to mess things up for you. Okay, so it's also going to make a little compounds a little bit more difficult to look at, but if we got to focus, right? Tartaric acid, for example, we got 2 stereogenic centers here, right? I've drawn it in a very suggestive manner and super helpful, but let's say we've got some wedges and dashes in there now. This particular stereoisomer of tartaric acid does have a mirror image, right? So let's draw this guy out. Draw that wedge on the left and the dash on the right. Okay, so this is clearly a mirror image, or these two compounds are mirror images of one another. So let's go ahead and draw another stereoisomer of tartaric acid, and we give the OH, each of the OHs of the alcohol a wedge, and the mirror image of this will be looking very similar with 2 wedges for the OH, right? Well, it's not, they are mirror images, right? But it's very easy to see that they are actually identical compounds as well, right? We can also just say that they are superimposable, right? So they are technically achiral as well. And then they have 2 stereogenic centers, but it's achiral, and that by definition means that this particular stereoisomer of tartaric acid is a meso compound, and you can see the plane of symmetry right down the middle. The 2 compounds above are non-superimposable mirror images of one another, and so by definition they are enantiomers. One thing I also want to note is that the upper left compound and the lower left compound, as well as these are actually, they're identical compounds, the one on the bottom left and right. And so let's erase these real quick because that's silly. But the bottom compounds are diastereomers of the upper 2 compounds because they are non-superimposable, non-mirror images of those 2. And so technically A and B are diastereomers of C. Okay? Non-superimposable, non-mirror images, aka diastereomers. All right, so we can also look at the configurations of these chiral centers. So let's look at this one, 1, 2, 3 for assignments, and then that rotates clockwise since the hydrogen low priority 4 is in the back, and that gives it the R configuration. Now, let me get rid of these numbers for you, make it more clear. The stereogenic center on the left has the hydrogen pointed towards us, and so we're going to have to use our hand on this one, but we still have the same assignments. And since we have to use our right hand to projecting towards us, our thumb projecting towards us, and to represent the hydrogen, and then we rotate from the top to the left, and so we're closing with our right hand. That gives it an R configuration. So it's an RR configuration on the compound A. That means compound B is SS because the OHs are swapped. Okay. What I mean by that is we've swapped so the OH on the left is no longer a dash, it's a wedge, and the OH on the right is no longer a wedge, it's a dash. So therefore it's no longer RR, it's SS. Now looking at this circled carbon, we already did the assignments for a wedge OH right here, and that's an R. We did the one for the left, and that was an S. And then we can do the same over on the other compound, that's R and S as well. I mean, they are the same compound, and so This is one way to identify that they are actually the same compound because they have the same configuration at the same carbon. Okay, so same configuration means they are the same compound, provided all the other like substituents kind of check out and are the same. Okay. All right. So remember that enantiomers are opposite configuration at each of the stereogenic centers, right? And so if we look above, they are RR and SS, so that's opposite, and that's kind of confirming that those non-superimposable mirror images are in fact enantiomers, right? Now, let me switch to this poopy brown color for you. These two right here, when we compare these, we can see that the R's match up, but there's an RS comparison here. And so remember the definition of diastereomers is that it differs at least one of the stereogenic centers, right? We can also say that it doesn't differ at all of them, and also that it stays the same at least one of them. Okay, and so there's different ways of looking at it, however you want to look at it, but either way, that's a diastereomer, right? So what do you say we do some practice so we don't come time for the exam we don't fall on our butts like this guy, you know what I mean? Just tumbling, silly guy. Meso compounds, or nah. Let's see if this compound is a meso compound. Of course, pause the video and try it for yourself. I will draw 3. Yeah, we'll do 3. Now go ahead and pause it after this one and try for yourself. So I'll walk you through it right now, though. Really what we're doing when we're doing this is looking for a plane of symmetry. If you slice this bad boy in half, you will get a mirror image. The same thing on the left as the same thing on the right, so therefore it's meso. Now this one right here is not as obvious, so we can't slice it there. What about through the OHs, right? Or it's kind of not obvious, but what you can do is rotate. And what you have to be careful when you do this though, because you want to make sure you get your wedges and your dashes correct. But when you do, you have a wedge and a dash, as you can see, and therefore we do not have symmetry. Because when we cut it, we won't have a mirror we won't have a mirror image. Now let's try this one. Same thing. So what I like to do, I count the carbons, right? So there's 6 carbons in this particular compound. So what I do is try and make a ring, like a pseudo ring, and then make sure that you put your bromine or your substituents at the correct spot. So the bromine is on the 2nd carbon as well as the 5th carbon. And if you were to do this, I'm just guessing right here, so I'll go ahead and say like, hey, this is meso, but we also want to kind of make sure that we get that the way we've drawn that particular compound, we want to make sure that we've got it, the wedges and the dashes correct, because it's a little complicated when you're starting to rotate things around like that. So let's assign some configuration. Starting with the first bromine on the left, we've got obviously 1, and then the 2 is the longer chain, and 3 is the shorter chain. We end up rotating that to the right to go in order, and that gives it an R configuration. So the one on the compound on the right that's redrawn, it's the same configuration, and it's obvious because the bromine still has the wedge, and we haven't really changed much. But the compound, the stereogenic center that after that is what we did change, and so we want to make sure that's correct. Now, if we set up our configuration, or what are we setting up? We're setting up our numbers, our priority assignments, and then we end up getting an S configuration. And if we do this one over here, we also get a 1, 2, 3 rotating to the left in this case, and that is in fact an S configuration, so it matches the compound on the left. It's RS as well as RS. Okay. Now the reason why the one on the left is rotating in a different direction is actually rotating clockwise, but remember that 4th priority is projected out towards us, so we like to use our left hand to and close in on the 1, 2, 3 to give it an S configuration. Okay, so it's meso, and I drew it properly. Yay me! All right, so draw meso compounds. So for each of the following structures, so we're gonna draw a bunch of structures, and then we want to draw some meso compounds for this. Okay, so we'll have to identify first our stereogenic centers, and here right, so pause the video if you want to try this on your own first, and then check to see what I do. So remember, like last time, count the number of carbons and make the ring. This time I want to make the ring kind of pointed upright like this so that it's more aesthetically pleasing. Put the bromines on the end, and then we have 1, 2, 3, 4. So the chlorines are on the 3 and the 4 position. And so this is all good right here in terms of the substituents. Now what we want to do is add our stereogenic centers, our wedges to our stereogenic centers. Keep them in the same direction. That way we can ensure that we have a plane of symmetry. The bromines aren't a stereogenic center, so that's why we don't have a wedge there. And that is the meso compound. There's a symmetry there. So this one only has 5 carbons now. So I started to draw a 5-membered ring, but didn't close it. And now we've got the 1, 2, 3, 4, 5 at the 2 and the 4 position. And then our mirror image is straight down that center again. So 1, 2, 3, 4, 5, 6 carbons for this one again. It's easy peasy when you do it like this. You know what I mean? It's all about that lemon squeezy. 2 amines on the bottom. We got the carbons at the 2 and the 5 position. Give them both wedges. You can give them dashes too if you want. It really doesn't matter, actually. If you rotate all of these molecules, you're going to get the dashed version of those substituents. And so there you go. All right, let's try another problem. This one is different. So if 2 stereogenic centers of a compound are R and S in configuration, what are the R and S configurations of its enantiomers and 2 diastereomers? So we have 2 to the N is 4, right? So that's, 2 to the 2 is 4. If we have 2 stereogenic centers, right? So we just give all combinations. The R and S, if we swap the configurations of each of those, we get S and R. Those are the enantiomers. And for the diastereomers, we just have to remember that we only change one of the configurations of those. So we can keep an R and then change the S to an R. And then so we get R and R, and then do the same to the bottom compound and do S and S. And that means we have diastereomers. Okay. So let's try this compound. How are sorbitol and compounds A and B related? Funsies. So what we're going to do first on this one is we're going to do 2 ways. We're going to look at the R and S configuration of each stereogenic center, and then we're also going to look at the wedges and dashes and see how those are changing and try and figure it out that way. So indicating the stereogenic centers here in red. Also, real quick, fun fact about sorbitol, that's the sugar alcohol in prunes that makes you poop. So, but back to chemistry. Well, everything's chemistry, just so you know. So, OH group obviously gets the priority. Now, the tricky part is figuring out the second and third sometimes, definitely in these middle stereogenic centers. That carbon on the left, it has an OH bound to it, while the carbon on the right has an OH and then another carbon. And so that's why the carbon on the right gets second priority. The hydrogen obviously gets the 4th priority, and that gives it an R configuration. Okay, so let's go ahead and we got to erase these numbers. So it's going to get real congested here. Let's take a look at that next stereogenic center. So the OH gets the first priority again. Now, as we go to the left and the right, we each have a carbon that's bound to an OH, right? Directly, it's very obvious. Those are looking very similar. But then we have to keep going until we find the first difference, okay? So the blue dots are indicating the carbon. So if we go to the one more to the left and the right, if we look at the one on the left, we have an OH, but there's 2 hydrogens on that carbon as well. And then the far right, we do have an OH there, which is similar, but we also have this extra carbon here, right? So that extra carbon beats basically the hydrogens that are present on the compound or the carbon on the left. So that gets the second priority, and then the one on the left gets the third priority. Now, I know this is going to be weird for you guys, but it's just going to take some practice. Try it on your own. And that rotation to the right gives it the R configuration. Okay, so now let's get rid of these marks so that way we can get the next two stereogenic centers, right? So obviously the OH is going to get that first priority again, right? Let's focus on that pretty in pink carbon. That OH gets number one priority, and now we got to look left and right. Well, it's the same thing. It's got an OH, so we got to go one more carbon over on the left and the right. And so what that's going to look like, and focus there, we got an OH and a carbon, and on the right we have just an OH and some hydrogens. So it's very similar to the last one. So the substituent basically coming off on the left is going to be the second priority, while the substituent on the right is going to be the third priority. That hydrogen is projected in the back. So that means in order to go from 1 to 2 to 3, we are rotating clockwise, which gives that pretty in pink carbon, that stereogenic center, it gives it the R configuration. Okay, so let me erase these. Got that R. Got that R. All right, so let's do this last one. What color do we want to do? All right, let's just do this. We'll do black. This stereogenic center right here. OH gets the 1, then we got 2 to the left, and then 3 to the right, because this 3 to the right only has OH and 2 hydrogens, while that 1 to the left has a bunch of carbons. So that gets the S configuration. So we have R, 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 S. Okay. So now let's try to figure out the configurations for A. Let's do it faster this time, okay? As if it wasn't fast enough already, huh? So let's take a look at this carbon. Since we already did that one, it's the same setup, right? And so this is still an S configuration. So now let's look at the this blue one is still a wedge, so we're going to call that an R configuration. That's still a dash, so we're going to call that an R as well for the red. Now that pink one is very different, or it's got the dash instead. So what we want to do is number our priorities 1, 2, 3, and that's an S configuration because the hydrogen projected at us. So now what we have is this particular configuration is opposite, right? And it's opposite than the original sorbitol molecule. And if we kind of write it out, we have an RRSS compared to an RRRS. Okay, so notice the R and the S at this third position are different, okay? But all the others are the same. And so since we differ at one, at least one, but some must stay the same, that means that A is a diastereomer of sorbitol. All right, so the easy way, the quick and easy way, let's do that one. You know what I mean? Sorbitol is a dash going from left to right. It's dash, wedge, wedge, wedge. Okay, and I'm referring to the way the OHs are positioned, and we can do it this way. Let's do B. It's a wedge, a dash, a dash, a dash. Okay. Now, since we have wedge, 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 dash, 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 they're the same, and we only differ at, they're all opposite, right? So everything is opposite configuration, so that means that B isn't an enantiomer of sorbitol. Okay? Now, we can do this simply because the way that the structure is drawn out is the same, meaning like it's the OH skeletal structure is drawn the same. The only thing we've really changed is the direction of the wedge or the dash, right? And so, or the not the direction, but just the wedge or the dash. And so that's why we're allowed to do it this way, and simply just say that since it's a dash compared to a wedge, those are opposite configuration, and therefore it doesn't matter if it's R or S. We know that the configuration is switched, and so since it's switched at every single carbon, then that's by definition an enantiomer. All right, so hopefully that I know that was a lot. Meso compounds are pretty fun, pretty difficult unless you figure out how to draw them in a nice and orderly fashion to allow you to visualize that symmetry. Or you get really good at identifying the configurations. So do both because you're going to need them no matter what. Depends on the scenario. Also, remember to count your carbons and see if you can create a nice little ring to allow you to see that symmetry or produce that symmetry if you have to draw it. Okay. All right. Have fun with it. And yeah, that's it.